Thank you.
Okay. So hello, everyone. My name is Wenhan. So we're from UC Santa Barbara. So today I'm going to talk about our work DeepPath, a reinforcement learning method for large graph reasoning. So as for large graph, you can think of it as a very large data structure, graph data structure that represents large number of real-world facts. So the nodes in your graph will actually be linear entities. It can be a person, a country, or anything that has a meaning. And the edge or the link between those actually represents the relationship of corresponding entity pairs. So if you look at one small part of this large graph on the right, this actually tells us that the profession of Tom Hanks is actor. So this is also called triple. Each triple has a head entity, predicate, and tail entity. So when we talk about the reasoning, when we talk about reasoning and knowledge graph, a specific task we're interested in is that given a query node, for example, a famous TV program called Band of Brothers, and a query relation TV program language, we want to find out what is the answer to this query, which means what is language spoken in this TV program called Band of Brothers. So very simple question, right? So how can we find this answer from a very large knowledge graph? So the basic idea is that we first start from the query entity, and we follow a couple of reasoning paths that have similar semantic meanings as the query relation TV program language. And hopefully, this kind of path can actually lead to an entity that is exactly the answer to this query. So how can we find or learn this kind of reasoning paths from this kind of knowledge graph? So that's the main problem or main task of this talk. So speaking of relative work, there are two branches of methods. So first branch of method actually try to make use of all these kind of paths in the knowledge graph. So an early work called path ranking algorithm try to use random walk. We restart between entity pairs to find a couple of paths, and then compute this kind of random walk probabilities as a future for each path. So a following work also following this PI model, they try to replace this kind of random walk probability with binary features, which can reduce computation required by PI model. So more recently, with the repetition power of neural nets, some more recent work, mainly from Andrew McCullen's group, actually use this kind of recurrent neural nets to encode this kind of PI-like path into vector repetition, and then compute this kind of cosine similarity between the path and the correlation as a future for each path. So another branch is actually based on the distributed repetitions. So basic idea is that they try to map all these kind of relations and entities into some kind of vector space or matrix repetitions, and then define a score functions using this kind of vectors and matrix. So these are some models, very famous models. So the common thing about all these kind of models is that the training objective of all these kind of models is just to try to maximize the scores of true triples and minimize the score of fake ones. So if you compare these two kind of methods, we should say that path-based method is actually more interpretable, because people can actually understand the reasoning paths in the knowledge graph, right? But embedding-based method sometimes is actually more robust, because there's no guarantee that we can always find enough reasoning paths from the knowledge graph. So our approach is actually is more close to the path-based method, but we also find a way to incorporate this kind of embedding repetitions. So the basic idea is that we want to learn the path instead of just using random walks like in PI model. So we actually find a connection between this kind of path finding process and Markov decision process, because the path finding, if you go from a head entity to a tail entity, is actually a very natural sequential decision making process. So we try to train a reinforcement agent to do path finding and using this kind of knowledge graph embeddings to represent the states. And after we learn this path, we can actually use this path as Horn clauses or logical formulas to do reasoning. So just for a brief introduction about reinforcement learning, I think this morning Lando had already talked about reinforcement learning. So we just have a basic idea. We have an agent, and agent will actually take actions according to its observations, always mostly just partial observations about the environment, and it will take actions. So environment will also transit from one state to another state after this action taken by the agent. And at the same time, we also give back a reward signal to the agent, so the agent just can using this kind of reward to keep improving itself. So in our scenario, our agent is just multi-neural nets which map this kind of state representation, which is a real value vectors into a stochastic policy, which is a distribution over all the valid actions. And we model this knowledge graph as a Markov decision process. So for the component of this Markov decision process, we first have a state representation, which is a continuous vector constructed by this kind of knowledge graph embeddings, and action space which define all the valid actions. And transition probability actually define dynamics of this environment. We just compute this kind of transitions using the local structures of this kind of knowledge graph. And we will define a couple of reward functions in the following slides. So to be more specific about the states and actions, our states is just concatenation of current entity embeddings and distance between the target and current entity. And we use all the unique relation types in the knowledge graph as our action space. So to show you how a model actually works, we have this figure. So we have neural agents. This agent will start from the query entity, and we take actions, which is actually relation link in the knowledge graph. So this kind of relation link can actually lead this agent to another entity. So the agent will keep taking actions like this until you reach the target entity. And at this point, you also get a reward based on this path, so the agent can use the path to adjust its parameters to maximize this kind of reward. So for reward functions, we define three kinds of reward functions. So the first thing we want the agent to do is actually find the path that can actually reach target entity. Because there are so many relation links in the knowledge graph, it's really hard to find the right path to the tail entity. So we define this kind of global accuracy reward, which just gives a positive reward to the path as long as it can reach target entity. And based on some prior work, we also observed that longer paths in the knowledge graph turns out to be very noisy and also very computation expensive to verify during inference. So we define another efficiency reward, which is actually just based on the length of the path to encourage the agent to find paths with smaller lengths. And finally, there's actually many paths in the knowledge graph that have similar semantic meanings, which is actually redundant information. So we define a diversity reward according to this kind of causal similarity between paths to encourage the agent to find a path with different semantic meanings. So for training, we just use a Monte Carlo policy gradient, also known as reinforced, to train our agents. So the training objective is just to maximize the expected value of the cumulative reward that the agent can get from one episode of path finding. So since we are just using Monte Carlo policy gradient, which means we just use one sample to estimate the expected value, which is of course of very high variance. So there's actually some method like baseline or actor-critic methods which can actually solve this problem, but we actually find out this kind of policy reinforced actually works fairly well for our model. So the final reward is just combination of three kinds of reward. So however, in practice, this actually not works that well. So to show you what the problem comes from, if we just first look at some successful reinforcement learning applications, for example, the Atari games, we notice that the action space is actually quite small. They only have 4 to 18 valid actions. And even for AlphaGo, which is a model-based framework that uses Monte Carlo tree search to guide the agent, they only have around 250 added actions. But for typical knowledge graph, it is very usual that we can have more than hundreds or even thousands of unique relation types. So the action space or search space is so large, which makes it very difficult for the agent to do exploration in this environment. And this can further lead to very poor conversion properties. So I believe this is a very common problem in this kind of natural language processing applications. So we cannot say that we find a perfect solution to that, but we actually use a trick to make it work for our model. So the idea is actually from the imitation learning. So we try to use imitation learning to pre-train the agent. And the trick is actually very similar to the supervised policy learning in the AlphaGo framework. So if you remember AlphaGo actually used some kind of expert moves to pre-train this policy agent. So for our scenario, we first just retrieve a few paths from the large graph using some kind of search algorithm to use this path and use as example actions and give all the example paths a positive reward to do imitation learning, and we use the same policy gradient to train this agent. So to test proposed model, we actually use two different data sets. First one is actually based on freebase and is constructed from the FB15K dataset, but with redundant relation removed. And we also actually constructed a new dataset based on the lab-ending language learning system. So to process the dataset, we first remove some useless relations, like has Wikipedia link or generalization. This kind of relations in our dataset actually has low reasoning values. And we also add triples with inverse relations to a large graph, which can actually enable this kind of agent to go backward in the large graph. And for each reasoning task, we remove all the triples with this particular relation to build the training examples and test examples. So to show you how the supervised pre-training actually works, we test our data, test the pre-train agent using held out test set. So as you can see from these figures, we increase the training episode or training time of the supervised policy learning. The agent actually quickly learns how to find a path that can actually lead to the target entity, even though the agent has never seen this kind of entity pair before. So this also means that our stage repetition can actually generalize. And after this stage, we can actually retrain or fine-tune the agent using the defined reward functions. So after we learn this path, we use this path as horn clauses to do reasoning. So these are some examples of our logical formulas. So for the first example, the reasoning relation is film country, which means we want to find out what is the country speaking in the what is country of this film. So there's a reasoning path which tells us if we first can find an actor in the film and then find out the nationality of this actor, we can actually use this nationality to predict the country of this film. So to verify this kind of reasoning path in a logic graph between task entity pair, we actually use a bidirectional path constraint search. So the motivation is that if we, for example, if we just go from one direction, from the head entity to a tail entity following this kind of reasoning path, then it is highly possible that during some intermediate point of this path, we can encounter some kind of supernodes which has a large number of labeling nodes. So if you want to keep following this path, we need to illuminate all the paths following all these labels. This is very computation expensive. But if at this point we can actually go from other directions, and which means we can always choose which directions to extend the path, we can actually avoid these kind of supernodes problems. So to show you the result of link prediction, which means given the head entity and relation, you want to predict what is a tail entity. So this is a result measured by mean average precision. we can see that our method actually can outperform both path-based method and embedding-based method. And because our method is actually a very natural way to combine this kind of embedding representations and path-based method. So let's look at some paths. So first thing is that we notice that learned paths, most of the learned paths are of very small length. This is consistent with the diversity reward we defined. And to show you some example paths, let's look at this kind of example learned path. For example, for the first reasoning task, we want to find out the nationality of the person. And we have this kind of reasoning path. So if we look at the first reasoning path, this actually means, for example, if someone is born in Santa Barbara and Santa Barbara actually belongs to United States, then United States can very likely be the nationality of this person, right? So, and another example here is that for the third one is someone held his marriage ceremony in, for example, in Copenhagen, and Copenhagen is the capital of Denmark, then very likely Denmark will also be the nationality of this person. So another example here for the language of the TV program, if you look at the third path here, which means if you can find actor and we know the language of this actor, we can actually use this language of actor to predict the language of the TV program. Okay, so for conclusions, we are the first to apply this kind of reinforcement learning framework to do large graph reasoning. And by using reinforcement learning, we can actually control this kind of path finding process, which is impossible if you're just using random walks. And our method is actually combined path-based method and embedding-based method because we use knowledge graph embeddings to represent the states. So for future directions, these are some things we are really excited about. So first thing is that instead of just using this kind of human-designed reward functions, is that a way that we can actually learn this kind of reward functions. So we actually want to apply this kind of adversarial learning to train a discriminant model that can automatically give you reward, which can be more accurate. So another thing is that we notice for some relations, that's actually not enough reasoning path. So if we keep using this kind of path-based method, we can actually very likely will fail to find the answer. So we also want to apply our work to do joint reasoning with both large graph triples and text informations. So finally, just feel free to try our code and new data set. Thank you.
All right, we have time for some questions. Do you want
to? Hey, thanks for the talk. My name is Arash from Amazon. So first question I have, pretty quick. Did you compare with the RNN-based reasoning models?
You mean to use this kind of recurrent neural nets to encode the path?
Yeah.
We didn't compare that. The reason is that we actually, the goal we are focused on is that we try to find this path instead of try to find a good representation of the path. So we didn't try to compare this kind of recurrent neural net-based representations of paths to the reason.
Second question, so how does your model perform when the target is farther than a couple of hops away?
We actually didn't.
Like your examples were a couple of hops, right? Do you have any, like, did you do any analysis that if it's like 5 hops away?
We didn't do that. Yeah, that's a very interesting question. We maybe investigate that in the future.
Thanks.
Yeah.
Hi, thanks for the talk. Actually connected to, I don't know who was actually asking the first question. So we tried something similar in the web navigation with the Wikipedia and the recurrent neural net. So you can definitely use the policy using the recurrent neural net. And then that turned out to improve the performance quite a bit for us. And,
Okay.
yeah. And then the second
Yeah.
thing is that was it just a greedy decoding you're doing? Because after training the policy, you can do some kind of, let's say,
We are
research type of thing, right?
we're not using the pure greedy decoding because we actually try different times. So we, for example, for one path finding, for one entity path, we actually tried maybe 50 times or 10 times to do. So each time we are do greedy, we just not greedy, we just sample one according to the policy. So we are not doing greedy decoding.
So in that case, in the test time, how do you choose among those 15 possible sampled paths?
So we actually will train some linear regression model to give weights to each path we found. So we just pick the top path to show here.
Okay, so I've got a question as well. I'm curious, when you do this with reinforcement learning, and in this knowledge base, you'll have some nodes where you have multiple outgoing edges with the same label, sort of like a child-of relation and things like that. Is this something you filtered out, or how do you deal with that?
I didn't get that, sorry.
So when you have multiple edges going out of a node that have the same label,
What kind of label?
like the daughter of relation, or like starred in, like if someone appeared in multiple films, these sort of things.
So the label is actually just based on the two triples in knowledge graph. So when we do our experiment, we first remove all some triples, and from the knowledge graph, and try if we can actually reason about these facts using the remaining triples. So I don't know if that answers the question.
Yeah.
Okay, let's discuss it offline. Yeah.
I think we have time for one more question. In that case, let's thank the speaker again for a very nice talk. Thanks.